The OrongoDB NetworkX adapter helps developers export their OrongoDB graphs into NetworkX, the Swiss Army knife for graph analysis in Python. With the help of the Adapter Notebook Guide, we'll be covering NetworkX basics, OrongoDB to NetworkX usage, as well as NetworkX to OrongoDB usage. Timestamps are made available in the description should you wish to fast forward. Thank you for joining us, and let's get started. NetworkX is a Python package for the creation, manipulation, and study of the structure, dynamics, and functions of complex networks. You can load and store networks in standard and non-standard data formats, generate many types of random and classic networks, analyze network structure, build network models, design new network algorithms, draw networks, and much more. The standard NetworkX graph-like objects are created with one of the following lines. For now, let's work with a basic undirected graph. We use the graph constructor and rely on the addEdge method to build our network. You can also build your network by inserting multiple edges at once via the addEdgesFrom method, as well as the addWeightedEdgesFrom method. Finally, we can see that we can provide node attributes here, as well as edge attributes. There are a number of graph algorithms provided within NetworkX. These include shortest path, breadth first search, clustering, as well as isomorphism algorithms. For example, here's Dijkstra's algorithm with a sample graph. NetworkX also provides a simple interface to drawing packages and layout algorithms. You can rely on the default functionality of the draw method, as seen here, or provide further drawing specifications such as the layout function used, as well as adding colors. NetworkX uses a dictionary of dictionaries as the basic network data structure. This allows for fast lookup with reasonable storage for large, sparse networks. To maximize NetworkX usability, the OrongoDB NetworkX adapter creates NetworkX graphs of type multi-digraph. This class allows multiple directed edges between pairs of nodes, similar to how OrongoDB operates. This concludes the basics of NetworkX. For more info, you can refer to networkx.org/documentation. I've created my adapter using the Python Orongo database client, which points to a temporary cloud endpoint generated by the OrongoDB Cloud Connector package. Now that we have this ADBNX adapter object, let's take a look at OrongoDB to NetworkX functionality. OrongoDB to NetworkX usage provides three main functionalities: transition by graph name, by collection names, and by metagraph. In this first example, we take a look at OrongoDB to NetworkX by graph name. It's as simple as specifying the existing graph name in OrongoDB. In our example above, I've set up an endpoint using the Cloud Connector package, and I've imported some sample data regarding fraud detection datasets. Let's run the snippet. An alternative is to specify the list of vertex and edge collections that you'd like to convert. For that case, we use the OrongoDB collections to NetworkX method. Lastly, it is also possible to convert an OrongoDB graph into NetworkX by metagraph, which allows users to handpick attributes as opposed to bringing everything over. For this, we use the OrongoDB to NetworkX method. This concludes the basics of OrongoDB to NetworkX. Let's move on and take a look now at NetworkX to OrongoDB usage, which, given NetworkX's Wild West approach to graphs, will be slightly trickier. When it comes to converting a NetworkX graph to OrongoDB, it is required to provide a set of edge definitions used to specify the relationships between your vertex and edge collections. If you're already familiar with creating OrongoDB graphs through the Python Orongo driver, then this is not a new concept. For this example, we use the NetworkX built-in grid graph and create a 5x5 grid. We also draw it for visualization purposes, once again define our edge definitions, and use the NetworkX to OrongoDB method, providing the OrongoDB graph name, the NetworkX graph object, along with the edge definitions. From here, we can take a look at the OrongoDB web interface and inspect our created grid graph. We can also take a look at the edge collections and the vertex collections, so let's take a look at that. Later in this video, I will introduce the concept of the ADB and X controller, which lets us handle non-homogeneous graph conversions. For now though, know that a custom ADB and X controller is not required since this network X graph only has one vertex collection type and one edge collection type. Here's another example of network X to OrangoDB, where the network X graph contains divisibility relationships between numbers 1 to 100. Notice how in our edge definitions, we are intentionally separating the numbers into two collections, numbers j and numbers I. This is not intuitive, nor is it recommended, but I've done this to demonstrate a part of the adapter's functionality. Even if this graph has more than one vertex collection, a custom ADB and X controller is still not required here. This is because the network X node IDs are already formatted to the OrangoDB standard, so the built-in ADB and X controller will take care of node identification. Note how once again that the node IDs here are collection/key, which the adapter can use to parse out and identify which node belongs to which collection based on the edge definition value provided. As a result, network X to OrangoDB in this context is still fairly straightforward and easy to use. If we run the snippet, we can see that the adapter has successfully created the divisibility graph. We can also head over to our web interface and load a sample just to visualize some of the relationships in our graph. Finally, we can also take a look at the edge collection that we've created, along with the two vertex collections. Earlier in this video, I had mentioned the use of a custom ADB and X controller for when your network X graph is no longer confined to one vertex collection or one edge collection. Given this following network X school graph, we can see that we are dealing with three vertex collections: student, lecture, and teacher. We are also dealing now with four edge relationships: student to lecture, student to student, teacher to lecture, as well as teacher to teacher. Given this newly introduced level of complexity, the OrangoDB Network X adapter now requires the user to derive a custom ADB and X controller in order to specify how each network X node or edge should be treated. This is done in a maximum of 4 steps, where the last 2 are optional. First, given a network X node and a list of OrangoDB vertex collections defined, we must be able to identify which OrangoDB vertex collection this node should belong to. This is done by overriding the Identify Network X node method of the controller. Second, given a network X edge, its pair of nodes, and a list of OrangoDB edge collections defined, we must be able to identify which edge collection this network X edge should belong to. We do so by overriding the Identify Network X edge method. Third, which is an optional step, given a network X node, we must be able to derive a valid OrangoDB key value. I say this is optional because you can disable this such that the adapter creates custom key values for your network X nodes. The same applies for the network X edges. In step 1, we establish a system to identify the collection of an arbitrary network X node. We do so by splitting the network X node ID on the colon and grab the first element after the split. This is because we've listed our node IDs to have the collection name first, followed by a colon as the separator, followed by the key value of that node. In step 2, we repeat the same process but for edges. The behavior is different but accomplishes the same goal of identification. In this method, you have access to the NX edge, which is the network X edge object. You have access to the from NX node, which is the network X node object representing the edge source, along with the network X node object representing the edge destination. Both of these objects have the following 4 attributes, and this is done via the adapter logic. You have access to the original network X ID of that node, the equivalent OrangoDB ID of that node, along with the OrangoDB collection it belongs to, and the OrangoDB key value of that node. What that means is that you can provide custom behavior on a case-by-case basis so that you can check and derive and identify which network X edge belongs to which OrangoDB edge collection. So in this case, if we define a relationship between student and lecture, then we can say, okay, this is the attends relationship. We can also say, well, if the from and to collections of both of my nodes up here are equivalent and they're both equal to student, then we know that this relationship is classmate. And this classmate relationship has been once again previously defined in our edge definitions. So you have to make sure as a user deriving this controller, you have to make sure that these two values match up. We also do the same thing between teacher and lecturer, as well as teacher and teacher. Otherwise, we create an exception and say that we do not recognize these two relationships, just in case if we ever need a safety belt. Lastly, in step 3, given that we want to maintain the keys we've written in our network X graph, so for example, student 101, teacher 101, or lecture 101, then we can derive the keyify network X node and override that method in our custom controller. We tell the adapter how it can fetch that information, and in this case, it's a simple split on the colon value to retrieve the numeric key. This is what the final custom ADB-NX controller looks like for our school graph. We can see here that we've overridden the behavior for identify network X node as part of our step 1. We've also done the same thing but for network X edges as part of our step 2. And finally, as an optional third step, we wanted to preserve the key values of our network X nodes, so we overrided the keyify network X node method. From here, we can create our new adapter, providing the custom ADB-NX controller in the constructor, and then we can invoke the network X to OrongoDB method, providing the OrongoDB graph name, the network X graph object, our list of edge definitions, and the keyify nodes flag to be enabled. This last parameter is done so that we can make sure that our custom keyify network X node behavior is used in our adapter's transition from network X to OrongoDB. Let's run the snippet. Here we can see that our adapter has successfully created the school graph. So if we head over to the web interface, we can indeed see that once we load the full graph, we can see that our set of teachers, lecturers, as well as students are properly imported into the correct collections. We can see now that we have the following 4 edge collections, so attends, classmate, colleague, and teaches, along with the 3 vertex collections. Know that a custom ADB-NX controller for network X to OrongoDB functionality is almost always needed, at the exception of homogeneous graphs and graphs where the network X node and edge IDs are already formatted to the OrongoDB ID standard. Once again, that's collection name / key value. This concludes the OrongoDB Network X Adapter Lunch and Learn session. I've left some useful links in the description below should you be interested in learning more about the adapter. Thanks again for joining, and feel free to reach out for any feedback or inquiries. Once again, all the best.